Reciprocating compressor drive methods. Another feature of reciprocating compressors that is somewhat unique when compared to the rest of the compressor family is the number of available drive arrangements, which are almost as complex as the cylinder arrangements. Single and multi-stage arrangement. Small compressors, particularly the trunk type, are usually V-belt driven by electric motors. The single-acting crosshead type in the small, double-acting, single-stage compressors are also driven in a similar manner. Larger, multi-stage, trunk-type compressors can be sized to operate at common motor speeds and therefore are direct coupled. The larger, crosshead, double-acting, multi-stage compressors present the most variations in drive arrangements. If such a compressor has an integral electric motor sharing a common shaft with the compressor, it is called an engine type. These compressors can also be directly coupled to a separate electric motor in a more conventional manner. Gear units may be involved in the drivetrain where speed matching is required. Multiple frames are sometimes used with a common crankshaft in a compound arrangement to use a common driver. Variable frequency motor drives are becoming more popular because of their ability to provide capacity control. Reciprocating compressors are available with a large variety of other drivers, which include the piston engine, a steam turbine, or, in rare cases, a gas turbine. Next in popularity to the electric motor is the piston engine. The arrangement lends itself to skid mounting, particularly with the semi-portable units found in the oil field. The unit is also popular as a lease unit, which may be lifted onto a flatbed trailer and moved from one location to another as needed. The engine is either direct coupled or, as with smaller compressors, it may be belt connected. A variation of the smaller, skid-mounted, engine-driven compressor is a larger, engine-driven version in the form of the integral engine compressor. See Figure 3-4. The compressor and the engine share a common frame and crankshaft. When the engine cylinders are vertical or in a V configuration and the compressor cylinders are horizontal, the machine is called an angle engine compressor. Reciprocating compressors are used for the direct reliquefaction of vapor boiled off due to heat inleak. System complexity. Conventional state-of-the-art reciprocating compressors utilize double-acting pistons, each connected to a rod, crankshaft, coupling, and separate motor, driver. This arrangement is mechanically complex and relatively inefficient, as it consists of multiple moving parts that require bearings, seals, and lubrication, which can require frequent maintenance intervals. The fundamental piston actuation of the LMRC is achieved through magnetic forces. Since the LMRC replaces a crankshaft-type piston design with a sealed cylinder, deterioration of the wear bands is minimized and piston rod packing is avoided. Therefore, component wear and associated maintenance are significantly reduced. Mechanical performance. Due to the many moving parts of a conventional reciprocating compressor, speed variation and flow capacity control make it difficult to avoid vibration problems. Each moving part has its own natural vibration frequency and high cycle fatigue limitation. The LMRC uses fewer moving parts, and thus, it will be easier to design the system to avoid coincidence with component mechanical natural frequencies. Pulsation control. Pulsations generated by a conventional reciprocating compressor have to be damped, attenuated using pulsation filter bottles, orifice plates, choke tubes, and/or Helmholtz resonators, all of which add cost and complexity and reduce compressor efficiency. The LMRC will operate at very low speeds. As a result, pulsations are expected to be much less problematic, and most of the above-mentioned pulsation attenuation devices should not be necessary.